So thanks everybody for joining us this month for the Astronomy Fundamentals regular monthly meeting. This month, we will be having two presentations. Pete Hermes will be giving our constellation of the month on Horologium and Volans. After this month, we will only have two constellations left on the list until we have gone through all 88. Looking for some ideas as to what we could do after that. And then at the end of after that, we will be finishing up what has become a three-part series on star classification, going into some of the high-level details for white dwarfs, neutron stars, and neutron star variants. And hopefully this time it doesn't take me an hour to get through what is 20 slides like I did last time. So all good though. So Pete, with that, we'll kick it over to you if you want to go ahead and share your screen and your.
I will do that. Let's see. Thank you. It's always a pleasure to present before this esteemed group. And I'll tell you what, Connor, I'll go through mine real quick. I'll get done here in about 5 minutes so you can have the hour and we'll go from there. Okay. What does I have to do? Yeah, I think this will work out. Okay, anyhow, good evening. Pete Hermes here once again. We've got a couple of constellations we'll go over. Volans will be the first one. Both these constellations are in the southern hemisphere. So it's celestial hemisphere. We can see parts of one, and that's actually the Horologium. That'll be the second one I cover today. But without further ado, we'll go ahead and start with Volans. As far as some basic details about this particular constellation, it's in the southern skies. I mentioned before, it's one of the smallest, 76th in area out of 88 constellations, 141 square degrees. Ascribed to be a flying fish, basically the pattern, the format, what was seen by those, particularly those that were specifying animals or, other than human life in the sky. And I'll get to that a little bit more as far as who originally specified it. On the case of this particular constellation, it's never visible from Tucson because it lies below the minus 60 degree line on the celestial sphere, and can only be seen at latitudes between plus 15 and 90 on the surface of the Earth. Neighboring constellations: Carina, Chameleon, Dorado, Mensa, and Pictor. Not a whole lot, and with regards to unique attributes to this particular constellation, same for our second one, other than the fact there are two stars with known exoplanets. However, no Messier objects, no named stars, and no associated meteor showers. You can see my picture is a little bit blocked. Trying to move the crew around here. Just bear with me. I'm going to try to move a couple. There we go. Anyhow, when you look at, you can see the image on the left, of course, is the constellation when viewed near dusk. And you can see the layout is a little bit different. Very shortly, you'll see the diagram of the constellation, which you follow my cursor on here. I mean, basically, it's got the outline of a bow tie, which is typically what most of the outlines will be. This is alpha, beta, epsilon. I believe we have delta and gamma. And then a couple of other key stars in this particular constellation. There's also going to be, I think it's Zeta down here. Yeah, it is Zeta, which is another star. And sometimes Zeta is going to show up in some of the diagrams. And then we've also got Eta. What else do we have? Eta Kappa, and then my cursor keeps disappearing, Theta. So Eta, Kappa, Theta. But basically the outline sometimes is a fan, and that's what you see over here. You see this is Zeta down here, instead of it just going the bow tie to this star, then over. But anyhow, as far as the history of the constellation, doesn't ascribe to any mythical connections or origination. Here again, one of the southern stars. There are a couple of key folks, and this is one person other than Le Caillé, and we'll talk about him later with respect to Horologium. But this constellation was laid out by Petrus Plancius. He was a Dutch astronomer and cartographer. This would be late in the 16th century. This particular constellation is one of 12 that he laid out. Based on the observations done by some Dutch navigators, Pieter Dirkzoen and Dirkzoen Kaiser and Frederick de Houtman. It first appeared in one of Johann Barr's star atlases, the Uranometria, in 1603. Originally, it was known as Pisces Volans, the flying fish. Later, it was just shortened to Volans. In the mid-1800s, John Herschel suggested that, and subsequently, it has remained so, just the shortened version. Francis Bailey included Volans in his British Association catalog in 1845 with the short name, and it forever stuck. When the constellations were ultimately specified by the IAU early in the 20th century. At one point, the constellation, like I say, is representative of tropical flying fish in the air accompanied by the ship. And this dates back to some classical, I guess, constellations is the best way to put it. There was one identified in the southern hemisphere, Argo Navis, that actually included three other modern day constellations, Carina, Puppis, and Vela. Argo Navis was disbanded, so to speak, and split up into these other constellations. But anyhow, the constellation was viewed as, accompanying the ship and being chased by one of the other constellations nearby, Dorado. And so that's a little bit of the storyline behind it. Not much other than that, because like I said, there's no mythological association attributed to this particular constellation. Okay, you see the layout of the constellations, two different representations, one a little more classical with all the characters on the left, and then one on the right that shows all the key stars. And like I say, when you look on the one on the right, you can see it has more of a bow tie layout, but flying fish. And like I say, sometimes you would see it where they start in Zeta, wrap it around, and that's what you saw in one of those first pictures that I started with. Interesting enough, I got something blocking here. Let me see if I can make a little move so I can move my cursor. Of course, Carina's nearby, and this is Canopus. The second brightest star in our sky, in the skies next to Sirius, and so it's not too far away. However, generally, in the case of here in Tucson, we can't see much below 50, minus 50 on the celestial hemisphere. We can see Canopus occasionally during certain periods, but once you get below the 60 degree, nothing is visible really to us. Okay. Notable stars in Volans. Beta Volantis is the brightest star in the constellation, and of course here again it was located in the I'll call it the upper left, but probably the most northern portion of the constellation. A paramagnitude 3.77. It lies just over 107 light years from our solar system. And in the case of Beta, it's an orange giant K star. Mass a little bit over, 1.5 times our own sun. However, the luminosity is 41 times our own sun. Gamma Volantis towards well, my pictures are just not showing up as good, so I'll prefer. But gamma is down as in this area, sort of like in the southwestern portion. Anyhow, it's a binary. Primary gamma 2 is an orange giant, 3.78 apparent magnitude, and the secondary gamma 1 is a yellow white main sequence F star. If you're able to see this here again, we can't, but it's something that would be usually very easy to split, probably with a with a 4 or 5 inch telescope, because it's 14 arc seconds of separation. And this particular system lies about 142 light years from the sun. Zeta Volantis is a binary, also orange giant, K star, and a 10th magnitude companion. Total apparent magnitude of 3.93, 134 light years from our solar system. Delta Volantis, a yellow-white giant F star, 3.97, 660 light years see, there was a trend going here where they were basically within about 100, 200 light years, but this one is, in the case of Delta, is substantially further out. Alpha Volantis, and I'm going to come back to this a little bit, and I'll fumble through it a little bit, so certainly Connor, anybody else that's a little more knowledgeable. But this is a unique kind of star. It's an AM metallic line star, A-type, chemically peculiar, with strong spectrum and absorption of metals. The type star, and I'll come back to this again because I think it's on the next slide a little bit about metallic line stars. But basically, the K, the H, and the M will represent calcium, hydrogen, and I think, the other metals. But anyhow, when looking at the calcium lines in the spectrum, it manifests as an A3 star. When looking at the hydrogen lines, it appears as an A5 star. And when looking at the other metal lines in its spectrum, here again, it manifests as an A5. Magnitude of 4.0, 125 light years away. Relatively young star, only 427 million years old. So probably what, I think our sun is right, a little over 4 billion. So we're talking basically about a tenth of the time. In the middle of the constellation, center of the bow tie, I'll call it, or the center of the fish, is Epsilon Volantis. This is a triple system. The primary is a blue-white subgiant B star. Then the spectroscopic binary with another star where the period is a little over 14 days. The binary portion also has an 8.1 companion, 6 seconds away, kind of tight, would be a little difficult to split, but could still be done with a 5-inch scope. And the combined apparent magnitude 4.35, 642 light years away. Now, here again, this is a point for discussion, so I'll certainly let anybody with a little more knowledge get into it. But I researched a little bit on AM or metallic line stars. They're kind of unique. Like I say, they're chemically peculiar with respect to some of the substances. Strong and often variable absorption lines of metals, for instance, zinc, strontium, zirconium, and barium. Not always, but those are just some of the examples. And deficiencies of others, such as calcium and scandium. The classical definition, early on when AM or metallic line stars were first specified, I guess, is an underabundance of calcium and scandium, and an overabundance of elements, iron and heavier. Abnormalities due to these elements, which absorb more light, being pushed to the surface of the star, and others sinking because of gravity, assuming low rotational velocity. And my understanding is the low rotational velocity could be affected by the tidal breaking of the companion star. Some other examples, of course, the brightest star in our sky, Sirius, is also an AM or metallic line star. A couple of other examples, Castor, along with Alpha Volantis, of course, Acubens, Kurhan, a couple of others. If you take a look at the the star chart, the Hertzsprung-Russell chart on the right, and I don't know if it shows up real good with what you're seeing. It isn't showing up real good, so if I take my cursor, but basically, Alpha Volantis will be on the diagram right about where my cursor was there. It has a tendency to disappear. I don't know. Can you all see this? Where I'm pointing right now?
I can.
Yes.
Okay, so that's where it would lie on the diagram, just to give you an idea. And that's, this particular star, where the others would lie, I'm not quite sure. I know some were a little bit bigger. But anyhow, little information on AM or metallic line stars. Connor, you got any other input on these stars, or you have any other knowledge?
I
about them,
haven't.
Doug,
I haven't
else?
run across these stars before.
Oh, okay. 'Cause I thought
It sounds like they're mostly a population 1 type star, given their variation of elements, especially elements heavier than iron.
Yeah, one would think so, but I'm not. When I was researching it, that was not evident, and that was certainly a question I had, and I wasn't able to answer that, because certainly I would think that would be the case, but I don't know. It may very well be. I'm just not sure. That did not come up in the basic information about these particular stars. Okay, so moving on, a couple of other notable stars in the constellation. Eta Volantis is a triple with a white subgiant primary A, and then 2 12th magnitude companions. The companions are 30, respectively, just over 30 and 42 arc seconds away from their primary. The entire system manifests as 5.28 apparent magnitude and lies 356 light years away from our solar system. Kappa Volantis is another triple, blue-white giant B star, 5.33 magnitude, with a white subgiant alpha star, 5.63, and a magnitude 8.5 unspecified star, about 37, just over 37 arc seconds away. The main components of this triple system, the blue-white giant and the subgiant Kappa 1 and Kappa 2 respectively, are separated by a good distance, just over an arc minute, 65 arc seconds. Theta Volantis lies a little bit below the bow tie, a little bit to the east, southeast of Epsilon, is a white main sequence, A star, about 239 light years away, manifesting just over a fifth magnitude. Iota Volantis, a blue-white subgiant, B star, 5.41, 558 light years away. Then the final notable star, somewhat similar to our sun, HD 76700, was it Henry Draper, I believe, catalog, which is an older catalog from the early parts of the 20th century that cataloged basically up to about 9th or 10th magnitude stars. But however, it was one of the first catalogs that started including spectral information on stars. But anyhow, this is a yellow dwarf G star, 8.13 apparent magnitude, 194.6 light years away. Mass is roughly what our sun is, but is much brighter and older than our sun. And this is one of the stars that had a planet recently discovered orbiting with a period of just under 4 days. The mass of that planet, about not quite 25% that of Jupiter. Okay, deep sky objects. A couple of interesting things. NGC 2397, and that's the image just to the right there, is a spiral galaxy, magnitude of about 12.68, 60 million light years away. Nucleus is comprised primarily of old red and yellow stars. Outer arms have recent star formation. I think this is typical of a lot of spirals. This was discovered in 1835 by John Herschel. No surprise there. However, there was also a late-stage supernova that was discovered in 2006. Excuse me. Second item down, picture right next to it, is kind of an interesting image. Lindsay Shapley ring. It's an unbarred lenticular galaxy. Magnitude's right about 14. 300 million light years away. The ring is approximately 150,000 light years across, in diameter, believed to have been formed following the collision with another galaxy. Starburst area contains many hot blue stars. This was a late discovery, discovered by Lindsay and Shapley in 1960. Another interesting piece, kind of the interesting thing about these deep sky objects, they have some unique shapes or attributions associated with them, a little bit more than some other deep sky objects. The Meat Hook Galaxy, or NGC 2442, is an intermediate spiral, basically two big spiral arms. This was discovered here again by Herschel. Magnitude of about 11, 50 million light years away. In this case, the galaxy spans about 150,000 light years. In this case, I don't see a whole lot of distortion, but distortion is proposed to have been caused by an encounter with a smaller galaxy, not necessarily adjoining, but perhaps just a close by encounter. And then the bottom item, NGC 2434, is an elliptical galaxy, magnitude 11.3. This one is 22,000 megaparsec distant from us. It was discovered by Herschel in 1834. Okay, those are the references for this first presentation. Any questions, comments, anything? Hearing none, I'll go ahead and move into the second presentation. There we go. I'm going to see if I can move you guys. Oh, that's what I wanted to do. Okay, very good. Anyhow, our second constellation is HOROLOGIUM. Here again, another southern
Riley, I think you're still,
constellation.
you were presenting a PowerPoint and it's still on the Volans presentation.
It's still on that one. Okay, maybe I have
You
to
may
get
have to,
rid
you'll
of
probably
it.
have to
Hold
stop
on.
sharing and resharing because you were.
I see what you're saying. Okay, screen sharing stopped. Okay, and then go back into my other one. Oh, I know what I did. Here we go. Share screen. Okay. How's that look now, Connor?
Looks good.
Okay. So here we go with Horologium. Here again, another southern sky constellation. Horologium referred to the clock, and there'll be some other variations, Latin variation of the clock. A little bit larger than our previous one, 58th in size, 58th in size out of the 88 constellations, 249 square degrees. The northern 1/3 of the constellation is visible from Tucson, mostly at the end of December is probably the peak. At about 9 o'clock local time in the evening, lies between the -40 to -65 line, actually 67, and can be seen latitudes +30 to +90. So we can, like I said, we can see a little bit below that -50 line. So that's why we can see basically the top third of this particular constellation. Neighboring constellations are Coelum, Dorado, Eridanus, Hydrus, and Reticulum. No stars brighter than third magnitude, only one star within, in this case, most of the stars are kind of far away, only one star within 10 parsecs of our solar system or the Earth. 3 stars with known exoplanets, as with Volans, no Messier objects, no named stars, and no associated meteor showers. Brief history, just like Volans, no mythical connections or origination. This one was created, and we've seen this name before, and Nicolas Louis de Lacaille, who pretty much created this constellation in 1756, along with a good number of others in the southern hemisphere. Originally, it was known as Horologium Oscillatorium pendulum clock, out of honor of Christian Huygens, who was the inventor of the pendulum clock, and later it was just, here again, shortened to Horologium. A unique thing about this, and this will be the outlier for this particular constellation, is it's home to the Horologium supercluster, over not just 5,000 galaxies, 5,000 galaxy groups. This is a rather enormous and interesting piece of galactic space out there, and I have a slide towards the end that will speak to that a little bit more, some of the attributes and characteristics of the supercluster. Here's a layout of Horologium, pretty long, and you can see how it extends basically from -40 down to -67, going along Eridanus. And, like I say, we can see that part from about, Zeta Eta would be at the extremes, the lower portion, or NGC 1261, as you see on the diagram. That would be about it for us. So we would not see that lower portion, and would be pressed really to see that section just below -50. Notable stars in Horologium. Alpha is a giant K star, 3.86 apparent magnitude. It's the brightest in the constellation, and one of the relatively closer ones, 117 light years distant from our solar system. Our Horologium is a red giant, 100 light years away, 4.7. This is a Mira variable. Miras are typically pulsating variable red stars with periods of greater than 100 days. There's some conflicting information, and in this particular one, some of the attributes make mention of light amplitude over 1 magnitude. I think it's greater than that, maybe perhaps in the infrared, and it says 2.5 in the visual because, as you can see, with a period of about 407 days, it has a magnitude variation from 4.7 to 14.3, which is clearly more than 2.5. So, and I suspect that that is the more accurate piece of information. It's one of the largest variables, in our night skies, not Tucson's night skies, but in the night sky overall. Beta Horologia is a giant alpha star, 310 light years away. Strong absorption lines, metal star, it's a metal-rich star. Delta Horologia, an alpha star, 175 light years away, just under the 5th magnitude. Iota, mid-range in the constellation is a yellow dwarf, somewhat similar to our sun. It's a G star. Luminosity just twice what our sun is. Believed to have an exoplanet approximating the size, the mass of Jupiter, discovered in 1998 in near Earth orbit, or an orbit around its star, roughly 1 AU or 93 million miles out from the star itself. And then GJ 1061, I think this is in the Gliese catalog. So these are, stars that are generally within, 20 light years of 20 light years? Yeah, 20 light years of our solar system, but it's a red dwarf, just under 12th magnitude. Mass, about 10% of our sun. Luminosity, significantly less, only about 1/10% of our sun's luminosity. 20th nearest known star to our solar system. And of course, those in the Gliese catalog typically are some of the closest stars to our solar system. Deep sky objects, Horologium supercluster. Got another slide on this, but just some basic things. 500 million light years across the entire supercluster. And you'll see another picture of it. It's not a very good picture, but roughly in the sky, it's 144 square degrees, 12 degrees by 12 degrees. As far as distance of the various galaxies that are contained within the supercluster, ranging from 700 million light years away to 1.2 billion light years away. So these are some pretty deep objects, believed to contain approximately 5,000 galaxy groups. Included in those 5,000 galaxy groups are 30,000 giant galaxies and 300,000 dwarf galaxies. And this is also known as the Horologium-Reticulum supercluster. That's another name that it goes by. And like I say, more about that on the next slide. A couple of other deep sky objects, and what you see, NGC 1261, and that's the top rightmost image. There's a globular cluster, just under 13th magnitude, just over 10 billion years old. So pretty old object as far as the universe goes. 8.3 apparent magnitude, just over 53,000 light years distant. This was discovered by James Dunlop in September of 1826. Our Matador 1, a globular cluster, 398,000 light years away. Measures about 1.3 by 7/10 of an arc minute. Kind of dim, difficult to see, even if you were down there and were able to bring it in, but magnitude of 15.72 apparent. Named after Halton Arp and Barry Mador, who observed and ID'd the cluster in 1979, so a fairly recent discovery. This had previously been discovered by personnel at the European Southern Observatory with some of their facilities down in northern Chile, but it was given its official name and claimed by these other two gentlemen. Now, the final two deep sky objects, NGC 1512 and 1510. The picture you see to the right of those two is not a composite. That's how they appear. It's a single frame. It's kind of interesting because you'll take a look at this and you'll see NGC 1512 is a barred spiral galaxy. As far as looking, through the telescope, if you were able to see this, it'd be just under 9 by 6 arc minutes across, so pretty good area layout. 70,000 light years across, magnitude of 11 and 30 million light years distance. This was discovered by James Dunlop in 1826. And I thought it was kind of interesting because you look at the second one, NGC 1510, as a lenticular galaxy. It's 40 million light years away, so about a third greater away. Magnitude's a little less, only 13, and it's about half the size, roughly a little bit less, probably more like a third or a quarter of the size, but 3.2 arc minutes by 1.8. Linear diameter of 15,000 light years, and this was discovered by John Herschel in 1839. And the reason I said it was kind of interesting, it's not that I'm questioning anything, but when Dunlop was looking at 1512, I kind of wonder, and granted, I know his equipment was vastly different than what we're using today, what he might have seen or what he might have thought that object just to the right was, whether or not he just thought it was a star or perhaps something else, or didn't pay attention to it, noting that, Herschel identified it as a galaxy, roughly 13 years later. No doubt, maybe better equipment, better locations. I'm not sure what the issues were, but I just thought that was kind of interesting from a historical perspective, as far as the discovery of two deep sky objects, a few years apart, but noticeably different in what they might have seen, and just trying to guess or speculate on what Dunlop might have seen as opposed to Herschel. Okay, a couple of other deep sky objects. NGC 1483 is a barred spiral, 40 million light years away. Here again, even smaller in area in the sky, roughly 1.5 by 1.5, so about 2.25 square arc minutes. Magnitude 12.3, also discovered by James Dunlop in September of 1826. Milton's Galaxy NGC 1433, another barred spiral, and you see the image to the right. This is a Seyfert galaxy, just under 10th magnitude, 32 million light years away. Dimensions, linear diameter, about 60,000 light years across, discovered by James Dunlop, same year. Type 2 supernova was observed in 1985. At the time, the magnitude was about 13.5. Seyfert galaxies, if I recall correctly, are some of the more luminous objects, not necessarily in visual, but other wavelengths, in some case visual. And I understand basically they put out energy similar to what a pulsar might, but they're not pulsars. Generally, these galaxies are very luminous in the center, to the point, for instance, some of the Seyfert galaxies have the same luminosity in their centers as our entire Milky Way. As far as what processes are generating that kind of energy and that kind of luminosity, I'm not entirely sure. I'll open that up to anybody. The only other thing I remember about it is typically a lot of the Seyfert galaxies supposedly have supermassive black holes at their center. Any other comment on Seyfert galaxies? Okay. Moving on, NGC 1448, also cataloged as 1457, is an unbarred spiral galaxy. Active galactic nucleus, so it's an active galaxy. 10.7 apparent magnitude, 56 million light years away. You can see the dimensions here again, discovered by John Herschel in October of 1835. 4 supernovas observed in the past 2 decades, or a little over 2 decades. Type 2 in 1983, Type 1A in 2001, Type 2 in 2003, and a Type 1B in 2014. Evidence, I believe, of a supermassive black hole in 2017 was laid out for this particular object. Okay, a little bit about the HOROLOGIUM-RETICULum supercluster. Mass, 10 to the 17th suns, so it's quite huge. Everyone knows that's 10 to the 17 0, 10 with 17 zeros following it. More massive than our sun. Similar mass to the Laniakea supercluster, which includes our Milky Way. Includes galaxy cluster of Bell 3266, and you can see a bunch of others in there just laid out. It was first noticed by Stewart in 1899, then Carlo Shapley in 1935. For some reason, I think part of it is because it's in the southern hemisphere. However, there have been a number of observatories set up down there. It has not been extensively studied, and a lot of people don't know about this, even professional astronomers. However, there was one paper that was generated in 1983. There hasn't been a lot generated, and I just left the link on there. If anybody wants to take a look at it, might provide some interesting bedtime reading. Okay, references for that, and that concludes my presentation. Of course, I always have the stellar classifications at the end. Thank you. Connor, you awake?
Yep.
Oh yeah.
I was trying to find the mute button on my mic.
That was your time. That was your chance to get a nap in.
No, I had to find the mute button. I have a dongle. I'm trying to use it up. Thank you very much, Pete.
You're welcome.
Transition.
And you should have, I sent copies of those to you, I think earlier this morning.
I didn't see those in the email.
Okay.
Finding buttons. There we go. Okay. Moving right along it. Okay. There we go. Can everybody see my screen?
Yes.
Cool. So continuing where we left off last time, this is the part 3 in the series I've been working on for star classification, and it's exclusively on white dwarf and neutron stars. Come on, where's my mouse? There it is. So we're briefly, most of the conversation is to white dwarfs, neutron stars, magnetars, and pulsars, and we'll go through each of those in turn. Before we can get into these stars, we need to talk a little bit about physics. No math, just some conceptual stuff, because it plays a key part in understanding more about these objects beyond what you would normally have with nuclear fusion for other types of stars, main sequences, giant, subgiants, and then those types. So we need to talk a little bit about electron degeneracy pressure and exactly what that is. So stars are an ionized gas, a plasma, and as part of this, it's just this giant soup of typically hydrogen, and a bunch of free electrons in this gas. That's why it's ionized. The electrons are not orbiting, are not in stable orbits around any of the atomic nuclei. And electrons, by their nature, they want to be lazy. They want to go to bed, much like I kind of do right now. And they want to be consuming as little energy as possible. They want to be in an at-rest state, which is really hard to do inside of a star because everything is really hot. So the high temperature and the pressure that are found inside of a star, particularly near their cores, normally forces these free electrons to briefly orbit. They won't orbit long around atomic nuclei, just so that they can lose some of their energy. They'll briefly enter into orbit, shed some energy in the form of light, which is a normal thing that occurs when electrons will enter a state. They often give off a photon, which is what we see as a byproduct of all stars. And as the pressure inside of these stars increases, there's too much energy. The electrons are just moving far too quickly, and they're not able to enter a lowest energy state. Now, this comes to kind of key here, where with something called the Pauli exclusion principle, which in a very abridged version, it's a little bit more technical than this. It says that two electrons can't share the same state. It's a quantum state, really. But basically, you can think of it as you can't have two electrons in the same rough place. They don't like that. And so all of these electrons, because they aren't entering into stable orbits around these nuclei, they run out of places to go. And so they begin to start exerting their own pressure within the plasma to counteract the pressure from gravity. So pictorially, on the far left here, it's kind of the little grayish dots are representative of an atomic core, and the orange is roughly the electron cloud around these atoms. And the black dots are free-floating electrons in this plasma, and they're just bouncing around all over the place. And eventually they're going to just run out of room to maneuver because there's just so many floating in all of these gaps. And this is here because of this, and this where the Pauli exclusion principle comes in, is because they can't be in the same state, they start to put pressure onto each other. Now, after a certain point, once you get even more pressure, the electrons, which we'll talk more about here in a second, kind of disappear. We'll talk more about exactly what happens to them later. And all that's left here is a bunch of neutrons, which is where the neutron stars come from. And basically the same principle here. These neutrons don't, Pauli exclusion principle still applies, and these neutrons don't like to overlap with each other. Questions? It's kind of a very short, abridged version of degeneracy pressure, and it can be kind of confusing. There's a lot of conceptual physics in it. Okay. Moving on. So white dwarfs are the remnants of stars, much like our sun. Typically, the parent star that forms the white dwarf will be at or below 10 solar masses before, well, that star is on the main sequence. Excuse me. The white dwarfs themselves are roughly the size of Earth in volume, but they're packing as much mass as the sun in that volume. So imagine if you just take the sun, squeeze it down into a ball the size of the Earth, and that's kind of a neutron and a white dwarf star. Sorry, I thought I heard somebody say something. So on the upper end of stars that can form a white dwarf, these stars will typically lose mass as they go and transition into the giant and supergiant phases as part of their evolution. Our sun will also lose mass in this way later on in its life. And this mass loss will result in what we see as a planetary nebula. For those who are familiar with the Messier catalog, the Ring Nebula, Messier 57, is an example of a white dwarf planetary nebula, as well as the Helix Nebula, which is, I think it's the Helix Nebula, yeah, which is another very prominent planetary nebula that you may have seen in photographs. So white dwarfs are, instead of being comprised of normal plasma, like their parent stars were, they are instead composed of electron degenerate matter, which basically, as we mentioned, is kind of like this weird soup of electrons that don't really want to bond anywhere with their atoms, and that creates this pressure that resists gravitational collapse on the star in lieu of nuclear fusion. So these stars are no longer fusing the elements like they were as when they were on their main sequence or in their giant or supergiant phases, and it's just purely pressure from this electron degenerate matter that is keeping the stars from collapsing any farther. White dwarfs top out at 1.44 solar masses. This is something known as the Chandrasekhar limit. It ties a little bit into black holes, so I won't go much into it here. We've done some presentations on the Chandrasekhar limit in the past on black holes. Any heavier than this limit, the white dwarf will transition into a neutron star, or it could explode as a type 1a supernova. As I had briefly mentioned, these stars are no longer sustained by fusion, but the pressure from all these free-floating electrons in this plasma soup. They are extremely hot objects. I couldn't find a temperature reference here. I assume many millions of degrees on the surface, and they are slowly cooling over time since they don't have fusion to power them any further. They're just slowly bleeding off energy, radiating it out into space, and eventually they will cool down into what is proposed as a black dwarf. But we can't really confirm it, the existence of black dwarfs. They're purely theoretical at this point, and simulation estimates say that it will take about 14 billion years for a white dwarf to cool enough, and the universe is nowhere near that old. So another thing that we'll have to wait a couple of billion years to see if we're right, much like what happens to red dwarf stars. A couple of other alternative scenarios arise with white dwarfs in terms of how they kind of interact with the rest of their neighborhood. Oftentimes, a white dwarf will be a companion star to another star, like say a red giant, or just another general type of star. and they may orbit close enough that the white dwarf and its companions can start exchanging mass with each other, interacting gravely, and they will just start ripping off material. This can happen in two ways. One is the white dwarf could be stealing mass from its companion. The other is the companion could be stealing mass from the white dwarf. In the first case, where the white dwarf is the one that's doing all the stealing, this is what eventually triggers a type 1a supernova, which is what's commonly used as a standard candle in astronomy to help establish the distance scale in the nearby universe. In the other direction, and the articles on this weren't really well explaining about what these objects are. So take this with a grain of salt. But when the companion star is the one that is stealing material from the white dwarf, it can steal enough material that the white dwarf essentially goes into a planetary scale object, becoming what they was referred to as a helium planet or a diamond planet, which wasn't really well defined. And the articles I saw weren't really explaining what they are in great detail. So I do recommend, if you're interested in learning more about that, spend some time on Google and go chase some articles down. So kind of demonstrating where we're at here in the overall scale of the star's life cycle. We're down here with white dwarfs in the bottom half of this diagram. So we have this low mass star, and it transitions into a planetary nebula and a white dwarf, or we have it with the binary companion, and we can get a type 1a supernova or just a nova, which we're not going to talk about either of these here. And then conversely, for stars faster than that, we have neutron stars and pulsars, which we'll talk about here next. Any questions on white dwarfs before we move on? Any comments? Okay. So moving on to neutron stars, they're kind of the big brothers, relative of white dwarfs. They are a result of stars between 10 and 25 solar masses collapsing into these remnants. Anything heavier than 25 solar masses typically becomes a black hole. These stars, as part of their transition, when these stars are massive, so they'll almost always transition into a supergiant phase, and they'll start going. Once they run out of fuel in their cores, they'll start triggering a core collapse, which creates some interesting physical effects, like many things. And the pressure during this is so high that these electrons, these free electrons that would have been provided electron degeneracy pressure in the case of a white dwarf, there's so much pressure during this collapse and shockwave, which I have some diagrams here to show this off here in a little bit, that the electrons fuse with the protons to form in the star to form just neutrons. So a normal atomic nuclei within a supergiant, you're going to have carbon, heavier elements, helium, where it'll have, proton and neutron pairs. And all of the free electrons that were inside of the star convert the majority of the protons into neutrons. So you go from having this normal matter of, helium, carbon, and it's just this pure giant ball of super dense neutrons. In the same way that the electrons provide this degeneracy pressure to prevent the star from collapsing, the neutrons are the source of this pressure. They were first proposed by Walter Bade and Fritz Zwicky in 1934. And their first detected observation was 1967, and our good friend, the Crab Nebula, also known as Messier 1. and cataloged as supernova 1054. So it's also interesting that our first detection of a neutron star was also a pulsar. We'll talk more about those here in a second as well. So the way you form a neutron star is you take a supergiant, and supergiants will have this inert core, and around this inert core will be this layer of fusion. We'll have a diagram of this here in a second. So this is known as this burning shell layer. And this burning shell is what's fusing and adding additional mass to the inert core. This inert core, like the neutron star, has its shape maintained by degeneracy pressure. So there's nothing in there. There's no fusion in this core to resist gravity collapse. This degeneracy pressure is what allows it to keep the core stable. And this burning layer, where the actual fusion that's keeping the star alive, it's still undergoing fusion, and it's adding material, much like how in the sea you'll have this material that drifts down from the surface of the sea onto the seabed to start in order to provide nutrients for deep sea life. It's the same thing here. You have this trickle down effect of material in the burning layer that kind of just falls down into the core, where it doesn't undergo fusion. As part of this, I feel like that third bullet should have been a sentence. So at some point, this runs out of material here to sustain fusion in the burning layer, which triggers a further core collapse. And the temperature in the supergiant jumps tremendously up to 5 billion degrees Celsius, which is just a lot of zeros and a really mind-boggling number to just try to get your head around. Which actually causes, this was actually really cool, that iron atoms just disintegrate. They're just so hot, which is to me really crazy that an atom just ceases to exist. It just turns into alpha particle and gamma radiation. And during this, the star is still like collapsing as these iron atoms just kind of just disintegrate. And eventually, the strong nuclear force, which we won't talk about much here, will kick in, and it halts this collapse of the star further, putting it inside of this weird stable state where these electrons are just floating around. Not electrons, excuse me, these neutrons are left over. And this all gets kicked off as part of the standard supernova explosion sequence. There we go. So over here on the right-hand side, we have the example of a typical supergiant. We have this inert helium core. The star is not massive enough here in this case for this helium core to sustain fusion. So it just sits there in the center of the star's this inert core. And around that, we have this shell, this burning shell, which is really just where the actual fusion in the star is occurring to help maintain the star's equilibrium. And then outside is just the rest of this material that isn't undergoing fusion, but it will probably cycle into this burning shell layer over time. So as we move through it, the outer layers of the star start shrinking in onto the inner core. And it kind of leaves behind this shock wave on the outer level. You can imagine this for a second. It's kind of like when you take a balloon, cover it in ice, or like you put it in water and cover it in ice, so it has like this really weird ice shell that's left, and then you pop the balloon. It's kind of what's going on with this outer layer, where that ice is like this shock wave that's kind of, and then the balloon itself is what shrunk. So this inner core portion here is compressing, it's accelerating in towards the core. During this, it's giving off a whole bunch of neutrino radiation as part of the supernova sequence. And all of this gas, which is not part of the inner core, is getting heated. and creates an instability in the star, which tears out these outer layers here. So we have this normal material that's left outside of the core, and the shock wave just blasts out all of this other material into a nebula, like the Crab Nebula, and leaves behind this neutron star, excuse me. Questions before I continue? Kind of a lot to unpack there.
So a neutron star doesn't emit light?
They do, but it's predominantly in the ultraviolet range.
Oh, okay.
They're very ultraviolet and gamma ray heavy objects, so beyond normal visible light that we would be able to see. You might still see something just because they're giving off so much energy, but most of their luminosity is beyond human visual range. Excellent question. And that's also the same for white dwarfs as well. They're giving, most of their energy is given off outside of the visible range spectrum.
So what's the closest neutron star to us?
Ooh. I actually do not know the answer to that question. I would think the Crab Nebula, but there could be one closer. Because I think the Crab Nebula is a couple hundred light years away. It's in the close neighborhood. Neutron stars are significantly smaller in volume compared to white dwarfs. On average, they're cramming 1.4 solar masses of material into a sphere roughly 12 miles in diameter, compared to a white dwarf, which is the size of Earth. So super dense objects. They are very, very, very magnetic. I cannot stress that enough, just how insanely magnetic these objects are. Which comes into play more with magnetars, which we'll talk about here in a second. Mind-boggling amounts of magnetism. There also are the magnetic poles on these stars will often rotate independently. So it's kind of like a situation on Earth where the magnetic pole wobbles with respect to the Earth's normal geographic poles. So our magnetic pole actually changes position over time. That same effect here is at play on neutron stars, except that instead of taking tens of thousands of years for what was it, a couple million years or something like that, it's a long time for our magnetic pole to change its position. Neutron stars, it happens usually minutes. The whole pole is just rotating independently of the star. The gravity on the surface of a neutron star is about 200 billion times that of Earth. You may have seen heard the anecdotal phrase that 1 teaspoon of material from a neutron star in terms of volume has the same amount of mass as the entirety of Mount Everest. Very, very dense, very high gravity objects. And their surface temperatures kind of reflect that intensity, with average surface temperatures of 600,000 degrees Celsius. Neutron stars, and pulsars and magnetars are also rotating very rapidly. As I skimmed over on one of the previous slides, as part of the core collapse process in the supernova, there you have the law of conservation of momentum still exists. And so as this star just sheds this outer layers from the go back. So this outer level of material gets torn off of the star. The core absorbs all of that momentum. And as part of the law of conservation of momentum, you lose mass, you gain speed. So this results in a very, very, very fast spinning neutron star. So able, you have this 12 mile diameter object that completes one rotation every, 1.4 milliseconds. That's a lot of velocity. What was really interesting is the fastest known neutron star for its rotational period is actually relativistic. It has an orbital speed of about 24% of the speed of light. It's a lot of speed in these objects. It's kind of just really nuts just how they really press, you know, your mind on is like, that's ridiculous. Moving on from neutron stars, we have their other variants, magnetars. So some neutron stars we found have stronger magnetic fields as a result of the rotation that gets imparted onto the neutron core as the supernova collapses to form these objects. So a normal neutron star has a magnetic field of about 10 to the 4 to 10 to the 7 Teslas. The Tesla is the standard unit of magnetism. Most magnetic fields you encounter in your day-to-day life are less than 1/10 of a Tesla. So 1 Tesla is a lot of magnetism. For additional reference, the magnets used in the super collider by CERN, those are rated at about 16 Tesla. And it turns out that the magnets used by the CERN super collider are enough to levitate a frog while it is still alive. So a magnetar, which has a magnetic field strength of 10 to the 8th to 10 to the 11th Tesla, that's a lot. These magnetars have magnetic fields that are so powerful that normal chemistry essentially just stops. The magnetic fields just simply rip off electrons, which are one of the key components in any chemical reaction. It's always an electron exchange. And so we just don't understand the chemical properties of what happens here. Taking an excerpt, magnetic fields are so strong that X-ray photons are regularly split into, or they merge together. The vacuum in space itself is polarized, becoming somewhat like a calcite crystal. I didn't quite understand the implications of that last portion. And atoms are, you know, much like how you would be in a black hole with like the spaghettification, the magnetic fields around a magnetar trigger some level of spaghettification on normal atoms. Now so it's just a lot. And this is even when you're 1,000 kilometers away from the surface of a magnetar. It just still blows my mind just how insanely powerful these objects are. It's just, you could go on for hours about the physics of these. It's crazy. Thankfully, though, these magnetars are typically short-lived. We think they're an intermediary phase in the evolution of neutron stars. The magnetic fields decay over a short period of about 10,000 years, and then they transition into a normal neutron star or pulsar. They rotate much more slowly than normal neutron stars, about 2 to 10 seconds instead of 1.4 seconds. But we have also identified a couple of ultra long period magnetars which have an orbital period, a rotational period on the order of minutes. Excuse me. Need to catch my breath. In addition to all the crazy things that are going on in these objects, our sun and all stars have some type of star quakes of just vibrations of material on the surface of the star. They are essentially exploding bombs in space, so there's all these movement and motions that we can't quite see without the aid of more powerful telescopes. But in the case of magnetars, their star quakes trigger X-ray and gamma ray outbursts instead of coronal mass ejections like we might get with our star, with the sun. Depending on characteristics. A magnetar could also be a pulsar. And they are also one of the leading candidates for a highly transient phenomenon that's been detected over the last several years, referred to as fast radio bursts. For those who aren't familiar with this, they are essentially a fast radio burst is essentially what it sounds like. It is a highly luminous burst of energy in the radio spectrum that lasts, on the order of seconds. We're still trying to pin down exactly what physics are resulting in this large amount of radio energy. Magnetars or magnetic fields are one. I forget what the other two are off the top of my head. It's been a while since I looked at the research for them. So, discovery. So on March 5th, 1979, 2 unmanned Soviet space probes were hit by a gust of gamma ray radiation. And these probes had radiation detectors on them. I forget what their exact science purpose was. But they went from a normal background detection of about 100 counts per second to over 200,000 counts per second, in about the time span of a millisecond. This burst of gamma rays continued to spread out from there. And about 11 seconds later, a NASA probe Helios 2, which was in orbit around the sun, was hit by this blast of radiation, and then Venus, and then the Pioneer Venus orbiter at the time, before eventually this wave moved on to Earth, where the powerful output was inundated the radiation detectors on 3 U.S. Department of Defense satellites, which were used for nuclear arms control and nuclear arms testing, as well as several other satellites. Eventually, we had enough of these points here. Thought I had more about this, but given these sequence of events of how this gamma ray burst was detected, we could use all of these points to triangulate exactly where in the night sky this radiation burst came from, which led us back to the first magnetar. Much like how we currently use the LIGO and Virgo observatories to triangulate the positions of gravitational waves. We had so many satellites and detectors that were hit by this gamma ray burst as it moved through our solar system. We were able to really pin down exactly where this first magnetar was. And I thought I had more about it here. I'm sorry, I thought I had mentioned what the first magnetar discovery was. That must have been me not completing the slide. I apologize. Finishing up, what time is it? 7:30. Okay, so I shouldn't have too much longer left. Pulsars were the last on my list. I think I only have 3 or 4 slides. A pulsar is short for a pulsating radio source. They are a type of neutron star, but they don't have the magnetic field intensity of a magnetar. Their telltale characteristic is that they are exactly what they sound like. They are a pulsing light source in the night sky. Their rotation results in a jet being emitted from the star, which moves with the star's rotation, which as it moves across the Earth's field of vision results in this pulse. And this regular rotation is where this pulsation, what leads to which leads to their name. So yeah, they're identified from the light emitted by the star's poles, and as the star rotates, this pole does as well. Most of the neutron stars that we have cataloged in the night sky are pulsars, and the light emitted by pulsars, their timings are so accurate that they are used as a means of navigation. The Pioneer and Voyager probes, for example, have a gold plaque showing the sun's position relative to 14 pulsars, which you may have seen. I did not include an image of that, but you've probably seen an image of those gold plates, those gold discs on the probes and other stuff, other mediums. Pulsars were first identified by Jocelyn Bell in 1967 while she was analyzing data from a newly commissioned radio telescope that she assisted in building. Her supervisor initially dismissed the signal as a terrestrial origin, a common occurrence in radio astronomy. You have a really strong signal. You kind of assume it's from a local source that you haven't accounted for or identified yet. Like, for example, a microwave going off nearby. But as they eventually they were getting repeated radio pulses from this same object about once every 1.3 seconds, this pulsating radio source, which they being radio in nature, your first assumption, this can't be natural. This must be of some side of intelligent life. And so their discovery was first cataloged as LGM1 for Little Green Men 1 until it was determined that it was actually a natural radio source a couple years later, which they would as they cataloged it as a Little Green Men 1, and assuming need to collect my thoughts for a second. So they assumed it was extraterrestrial until they found a second detection. There we go, much better. Which in a different region of space. An interesting fact is that the first exoplanet ever discovered was in orbit around the pulsar. In addition to their use of navigation, the pulsars were actually so accurate in their timekeeping with their orbital positions. They were actually more accurate than some of the first atomic clocks. And being a type of neutron star, they share many of the other characteristics. Oh, nope, I had a couple more slides. They share many characteristics with their cousins. They're all neutron stars, so they're powered by neutron degenerate matter, strong magnetic fields, high rotational velocities. But you can combine these two. You can have magnetars, pulsars, and neutron stars that are actually both at the same time, where it is both a magnetar and a pulsar. Where a neutron star will have the characteristics of both a magnetar and a pulsar. We currently know of about, as mentioned in this picture, we know of about 6 instances of this hybrid neutron magnetar pulsar object, of about 3,000 known pulsars, which that we detected, and about we've only found about 30 magnetars. And I think the estimate is that 10 of those, or 3 of those, are within the Milky Way galaxy. So magnetars are very rare objects, even compared to the rarities of neutron stars. You won't find them very often. And this is largely because, as I had mentioned, the magnetars are very short-lived. Their magnetic fields dissipate over the course of about 10,000 years. So at some point, many of the 3,000 pulsars that we see, they may have been hybrid magnetar pulsar objects at this time. They've just transitioned out of this magnetar phase. And with that, that wraps up all the star classification. Any questions or comments? There's a lot to unpack in some of those slides. Excuse me.
Yeah, it's very dense.
Pun intended, I take it.
From a punster, yeah.
From me, yeah.
Yeah.
Good presentation, Connor.
Yeah.
Yeah, good.
Again,
So it seems like if if you were to get close enough to one of those magnetars, that would be the end of us.
much they share that characteristic with our good friends black holes. You get near one, you don't live long enough to tell about it. But, we're more likely to get hit by a stray inert black hole parading into our solar system than a magnetar. So not much for us to worry about from that perspective.
Nope.
Connor, going back to white dwarfs, I wasn't aware that they was dense, but I mean, the main difference between a white dwarf and the neutron star, I mean, in the neutron star, you have that process where you're actually piling up neutrons, matter's being pushed into neutrons, and it's considerably more dense than the white dwarfs, yes?
So with white dwarfs, in both instances, you have a star that's exhausted its fusion material, and so with the pressure in it is gravitational pressure just causes it to collapse in on itself. With enough mass, in the case of a white dwarf, the electrons that are in it just kind of get stuck hanging around, and the electrons act as basically a pressure force to stop the gravitational collapse.
Okay.
And now in a neutron star, there's enough mass in the stars that they skip past that. So instead of having the electrons being providing this pressure force to resist gravitational collapse, the electrons merge with protons and turn into neutrons. And then the neutrons are providing this pressure to resist gravitational collapse and maintain the star stability.
So Connor, if I may interject a little bit.
Mhm.
The way it was always explained to me in early astronomy classes, and I think this is an easy way to understand it. In a white dwarf, you've got the atoms that make up the material in the core. They're compressed down basically to where the electron clouds are basically almost touching each other. That's as close as you can get them. The weak nuclear force prevents you from pushing them any closer. But if you think of the electron cloud and the nucleus, the electron cloud is mostly empty space, and you've got the little nucleus in the middle of the atom that's sitting there, but it's still mostly empty space. But you've compressed everything down as close as you can get without the electron clouds overlapping. In neutron star, what you've done is you've just pushed everything right down to where you've just got the nucleus of all the atoms compressed right up against each other. It's all neutrons now because the electrons have been forced into the nucleus to form neutrons, and it's all neutrons, and you're right up there where the nucleus are bumping into each other. That's a simple way it was explained to me.
Yeah.
So that's why it's so much more dense than a white dwarf.
Yep.
I mean, we're talking magnitudes more dense, right?
Yes.
Magnitude
Yeah,
more
okay.
dense. Yeah.
Earth size versus city size.
Oh, okay, same amount of mass, and okay.
Neutron stars can be a little bit more massive. Neutron stars top out at about 3 solar masses. Once they hit the 3 solar mass barrier, they transition into They would transition into a black hole. Versus a white dwarf, which would be 1.4 solar masses before they transition into something else. So thank everybody. It is kind of a difficult topic to wrap your head around. There's the physics and white dwarfs and neutron stars is a little bit more difficult to explain than just star goes, fuse material. Star goes boom, we're done.
Connor, excuse me, I kind of came in at your last couple slides there, but a question for you. On the white dwarf stage, since the electrons and protons haven't fused into neutrons, does that white dwarf state then, are those atoms do they represent a particular molecule? In other words, are they compacted uranium, or is
They
there an elemental level left?
they are predominantly helium atoms, because again, the white dwarf is the remnant of a sun-like star. It's the remnant of the core of a sun-like star. So this would be the leftover helium that was in the sun's core that could not be fused. So it's predominantly helium, but can include other heavier elements for slightly more massive stars. That's a good question. I thought I had called that out, but
I thought the last stage was iron.
That's in a really, really large supergiant star.
so white dwarf stars are not massive enough to result in iron fusion. They would typically stop out at helium fusion because they don't have the mass to sustain anything greater.
Ah, okay, gotcha. Thank you.
And with that, I'm going to go ahead and end the recording. And thank you, everybody.